Hi, I'm Younghoon. Today I'm really excited to present GraphScape, a model for reasoning about the visualization design space. This is collaborative work from University of Washington. To describe insight from data, an analyst typically generates many different charts, and so often must present a sequence of charts when communicating research to others. Similarly, in an area like data journalism, multiple charts are often shown in sequence in order to convey a story about data, as in this New York Times article about climate change. Both analysis and communications often depend on understanding multiple charts in sequence. So it is natural to ask, how might we sequence charts to better facilitate understanding? Let's start with an example. To prepare my trip from Seattle to Denver, I created some charts about recent weather. First plot is the number of sunny days in both cities. Here, Denver is blue and Seattle is orange. And I'm really excited that there are 3 times more sunny days in Denver. So that's good for me. But sadly, today is cloudy. Next, I compare the daily temperature. Seattle appears to be much more consistent. So I might need to bring a full wardrobe to Denver. Lastly, I plotted the temperature against the wind, and the wind in Seattle is more weaker than Denver. As I shared my finding, hopefully the order of charts was sensible. The first chart starts with the simplest comparison based on 2 data fields, so seems a good starting point. The subsequent charts each involve the 3 data fields and use the same encoding both region and temperature, and so it makes sense for them to be adjacent. If we jumble the order, the sequence requires more effort to understand. Charts sharing similar data fields and encoding are now no longer adjacent, and so the viewer must start over in interpreting each plot. There's another issue of how many sequences one might need to consider. In this case, there are only 6 distinctive possibilities. But as the number of charts increases, the number of potential sequences increases combinatorially. Given these challenges, how might we automatically recommend the useful sequences? In order to answer this, we will start by trying to answer a more fundamental question. How might we model the relationship among the charts? GraphScape is a model for automated reasoning about visualization, similarity, and sequencing. In this remainder of this talk, I will define what GraphScape is and share motivating applications and describe how we learn transition cost among charts and how we recommend the chart sequences. And finally, I will share our evaluation of the GraphScape. So, GraphScape is a directed graph model of visualization design, where a node represents a single visualization. We have implemented GraphScape using the Vega-like visualization language. So each node can be seen as a JSON Vega-like specifications, like the shown in the gray boxes. Edges represent a single edit operations that can transform any chart to another chart when combined. Here, the left chart is modified by adding a color representing regions. In other words, an add color edit operation. In addition, we assign to each edge a weight that represent estimated cost of chart interpretations. Given chart A, how it is hard to interpret chart B or chart C. In this example, the cost of adding color is greater than the cost of transposing the axis. This model can be used to support a number of motivating applications. First, given an initial chart, GraphScape can be used to search for alternative design. Let's say we want to draw a scatter plot, but it suffers from overplotting. GraphScape can conduct a graph search to find alternatives that reduce the number of visualized data values. A first candidate reduces the data via random sampling by applying an add filter operation. Continuing the search, we also find another alternative, a bin scatter plot. GraphScape can suggest more scalable candidate charts and then present them in order of transition cost. Another application is elaborating transitions passed between charts, for example, to enable animated transitions. To transition from chart A to chart B, a naive option would be simply interpolate between the two states. However, prior work has shown the complex transitions can be easier to follow if broke up into states, for example, through the intermediate chart C. GraphScape can be used to determine possible animation stages by determining intermediate plots. We can also apply GraphScape to recommend the order of chart sequence. Let's go back to our previous 3 charts about weather. We can enumerate possible sequences, calculate the cost of each sequence by a function of their transitions, and recommend the sequence with the lowest cost. To build a graph model of chart similarity, we start by analyzing the individual transitions between charts. We build our transition cost model in 3 steps. First, we identify all edit operations covering all possible edges in GraphScape. Second, we rank edit operations by hypothesis interpretation difficulty based on our expert judgment. Then we drive their edge cost via linear programming. Let's talk about each step in more detail. First, we started by identifying atomic edit operations that can express any transitions when combined. Then we categorize them into 3 groups. The first category is mark operations that change graphic objects like bar, point, area, line. Here, a mark operation changes a bar chart to a point chart. A second one is transform operations such as log scale, sorting, or filtering. Aggregation is also a transform edit operations. The third one is encoding operations, which change a visual encoding variable, such as x, y, color, shape, and size. Next, we ranked each operation based on our expert judgment of interpretation difficulty. We first ranked the overall categories, then individual transform they contain. To perform this ranking, we self-administered a set of triplet comparison tasks. In each task, a judge views the initial chart, then choose which of 2 charts is easier to understand given their initial chart. The result of each task is a linear inequality among edit operations. For example, if the judge decides a transpose is easier to follow than add color, we assume a lower cost rank for transpose. Lastly, we drive the cost of each edit operations by applying linear programming to our collected set of inequalities. However, because our model is based on our expert judgments, we must also verify it with external users. There are also some ambiguous rankings. For example, should we adding and removing filter have the same cost of asymmetry cost? And similarly, for adding and removing field from visual encoding variable. To refine our ranking, we conduct a controlled experiment where we wanted to resolve the ambiguous part of our rankings and test our modeling choices, and also want to see a users exhibit preference for global structures, such as whether people like a sequence that minimize the edit operations and prefer sequences that are grouped into repeating substructures. We recruited 51 students in graduate visualization course and asked to sequence 7 sets of charts. Here's the experimental UI. Participants use a drag and drop to sequence a set of charts as they want. Let me go through all 7 task designs and what we found from them. For testing ranking choices across the edit categories, we used these 2 sets. To compare mark operation with transform operations, we compare the highest and lowest ranked operations in those categories. In this case, we compare the point-to-light mark transitions and scale transitions. To compare transform operations and encoding operation, we compare a filter transition and transpose transitions, again representing the highest and lowest rank edit for their respective categories. In the result, participants validate our edit ranks. We also tested the ambiguous part, add and remove encoding and filter. And participants did not show a significant preference, so we decided to make them have the same weights. Upon the previous 4 tasks, we also make a task for making sure our ranks We also designed tasks to see a preference about global structure. Edit minimization is to check if people like to see a sequence having fewer edit operations. And yes, people wanted to see them. And drill down versus roll up is to find whether people want to start with an aggregate chart and then go to a row chart, or vice versa. And people show that they more like to roll up. Subsequence parallelism is to see if people also like to see subsequences with repeated transition patterns. And participants show that preference. And there's an extra finding in this task that participants always prefer the sequence with chronological order. Based on this finding, we model the sequence cost to recommend the sequence as the sum of transition cost. So we can evaluate this sequence cost as the sum of cost of two transitions, add X and add color. It is corresponding to the fact that people prefer the sequence having fewer edits. For example, people thought that interpretation difficulty of A is less than B, which has A's edit operations and one more extra edit operation, remove color. So B gets a larger sequence cost. But in some particular cases, it is not matched well. For example, sequence C, which is the reverse of A, has the same cost. But we thought A should have less cost than C, because A starts with a simple chart and add new information, but C starts with a complicated chart, then show a redundant chart. To match that, we introduced an empty chart at the beginning of each sequence, then counted the transition from the empty chart to first chart. For A, it is a single operation add X, but for C, it is a 3 operations, add X, add Y, and add color. So A gets less sequence cost than C. On top of that, we thought about the order of filtering values. Here are 2 sequences show the 3 charts filtered by 3 different years, and they have the same sum of transition cost. But according to our observations, that people prefer the sequence in chronological order. So A should have less cost. So we added the filtering sequence cost, which is a penalty cost for unsorted filtering values. In sequence A, filtering values are sorted, so filtering sequence cost is going to 0. And so sequence cost is just equal to the sum of transition cost. But sequence B, filtering values are not sorted. So B gets filtering sequence cost and gets larger sequence cost than A. This sequence cost worked well in some sense. There are 6 charts in 2 different years in 3 different regions. And this black path will have the minimum sequence cost as a 5 edit operation. But as we saw before, people prefer the sequence having the repeated transitions, like this, going through 1970s all cars, European cars, and USA cars, and then going through the other cars with the same order. Even the green path has one more edit operations than black path. We introduced a sequence weighting term as a discounting factor. It detects the repeated transition like these 2 changes of filtering values, then calculate how much these patterns cover all transitions. Here, the pattern covers 4 transitions among 6 transitions, including a transition from the empty chart. As a result, sequence weighting discounts the 4 sixes of the sum of transition cost and filtering sequence cost, which becomes our sequence cost. With this sequence cost, the green sequence gets less cost than black sequence. So we have evaluated our sequence cost through a control experiment. And I will skip the details because I'm running out of time. So we recruited 55 trackers and asked to rate each sequence in task. 1 is our GraphScape top choice, and 3 are handicrafted sequences, and 1 is random sequences. So we covered the previous research's transition taxonomy, measure work, dimension work, filter work, and we also make sure to have a subsequence parallelisms, and with 3 categories operations. Here's the UI. We filter out the people just giving 3 basic questions, and ask to think about the order, and ask to rate each 5 sequences in 5 Likert scale. And here's the result, and GraphScape's top prediction is among the highest rated in all but 1 cases, task 3. GraphScape grouped the sequence first by resent, then year, but the subjects preferred grouping primarily by year. And actually, the top and second highest related sequence in task 3 are also get high ranks among GraphScape's recommendations. And we also check the correlations among the two rankings, GraphScape rankings and participants' rankings. It is really highly correlated, and the subpart of rankings also correlated, but two components are not highly uncorrelated. So GraphScape enabled to automatic reasoning about the relationship among charts, and GraphScape can be applied to the find design alternative, to elaborate path, and to recommend visualization sequence. All implementations and basic APIs are available in our GitHub repository, so please check it out, and thank you for paying attention.
So I'd invite, if we have some questions, I have one ready. If there are nobody from the audience. So I would be interested to know how you plan to continue the research. I find this tool very useful, thinking that there might be different things that users might want to get out of the visualization. So they might have different type of needs and intents. And what kind of possible learning techniques, learning from the user could you apply to be able to account for that, to the fact that people might have different, goals in their head?
So the question is, how can we reflect the user's preference to make a sequence, or am I understand?
Yeah, right? I mean, just curiosity said in a much simpler way. Do you plan to be able to learn from different specific users about their different goals and needs in looking at the visualizations, so that you don't have a general rule that fits all, but you need to adapt and customize to different?
Yeah, that's interesting questions, and I also get a similar review from when I got reviewed, and I think it's really good future work, but we didn't categorize or parameterize the user's behavior or their goal, so we still have to do work for them, and yeah.